Welcome to The Explainer, where we break down big ideas. Today, we're going to talk about a dangerous lie that's kind of hidden in plain sight. It's the statistical trap that can make the best choice look like the worst one, and it can cost companies millions. Yeah, it's all about the massive problem with averages. All right, let's just dive right in with a real-life medical mystery. So picture this. You're a doctor. A patient comes in with kidney stones, and you've got two options, treatment A and treatment B. Your job? It's simple. Just pick the one that works better, the one with the higher success rate. Okay, so let's look at the data. For patients with small stones, you see treatment A has a 93% success rate. That beats treatment B's 87%. Okay, now for patients with large stones, well, would you look at that? Treatment A is also the winner, 73% versus 69% for B. I mean, so far, this is a total no-brainer, right? Treatment A is just better, period. It's winning in every single category. But then something really weird happens. When you combine all the patients and just look at the total success rate, the numbers completely flip. All of a sudden, treatment B looks like the better option, with an 83% success rate to A's 78%. So wait a second, how is that even possible? How can a treatment be better in both individual cases, but somehow worse overall? It makes no sense. So no, this is not a math error. What you're looking at is a classic, and honestly, a super tricky statistical trap. It's called Simpson's paradox, and it's a perfect example of how averages can totally lie to you.
So what exactly is it? Well, Simpson's paradox is what happens when you see a trend in a few different groups of data. But that trend completely disappears or even reverses the second you combine those groups. And it's almost always caused by some kind of hidden factor, what statisticians call a lurking variable that's messing with the results behind the scenes.
So, in our kidney stone mystery, that hidden, lurking variable, it's the size of the stones, which really is just a stand-in for how severe the case is. See, the size wasn't just a simple label. It was actually influencing which treatment the doctors chose and how likely that treatment was to succeed. And here's the real kicker. The doctors, using their best judgment, they tended to give treatment A, which was the better treatment, but maybe a bit more invasive, to the toughest cases. We're talking about the patients with those large, difficult stones. You can see it was used on 263 of them. And at the same time, treatment B, the less effective one, was used way more often on the easier cases, the ones with small stones. It was used 270 times on them. So because it got all these easy wins, its overall average success rate got this huge, totally artificial boost. That's why it looked so good when you matched all the numbers together.
So the crucial point here is that by averaging everything, we were comparing apples and oranges. It wasn't a fair fight at all. We were really comparing a great treatment used on hard cases against a not-so-great treatment used on easy cases. And the second you stop averaging and look at the groups separately, poof, the paradox just disappears. And it's crystal clear that treatment A was the better choice all along.
Now, this whole paradox thing, it's not just some quirky brain teaser for stat nerds. It actually points to a much bigger and frankly more dangerous problem that affects, well, pretty much everything. Business, finance, you name it. And this problem has a name: the flaw of averages. Sam Savage, a professor at Stanford, he just summed it up perfectly. The main idea is that if you make a plan based on a single average number, you're almost guaranteed to be wrong. Why? Because the real world is just never that simple. Savage uses this kind of dark but super clear analogy. Imagine a drunk guy staggering down the middle of a highway. His average position, it's the center line, perfectly safe, right? But what's his actual experience? He's weaving all over the place, into traffic. So the man at his average position is safe and sound, but on average, he's dead. The average completely, totally hides the real danger he's in. Okay, so what's happening here mathematically? Well, it's because most things in the real world don't follow a nice, simple, straight line. They have curves. And anytime you're dealing with a curve, like this one, the average of all the outcomes is not the same thing as the outcome you get from the average input. They're two different numbers. All right, let's take this idea and see how it plays out in a really high-stakes, real-world scenario. Let's talk about Hollywood and trying to forecast movie profits. Okay, so a movie studio is about to release a new film. They run the numbers, best case, worst case, most likely case, and they come up with an average forecast of about 766,000 ticket sales. Seems pretty reasonable, right? So they take that average number, plug it into their financial model, and it spits out a number.
They should probably set aside $1.6 million for estimated taxes. Simple, straightforward calculation. But come on, after everything we've just seen with the kidney stones and the staggering drunk on the highway, we gotta ask, right? Is that one simple average really telling them the whole story? Of course not even close. That average number completely misses a huge, non-linear part of the movie business. Think about it. If the movie is a surprise hit and sells more than, say, 900,000 tickets, what does the studio do? They push it to way more theaters. And sales don't just go up a little bit, they explode. A simple average just can't capture that kind of upside. So what happens when you ditch the simple average and use a better model, one that actually simulates the full range of possibilities? The result is pretty startling. The true expected tax payment is actually closer to 1.2 million, not 1.6 million. That means that one single lazy average caused the studio to overestimate their taxes by $400,000. That's a lot of cash they just tied up for no reason. And this brings us to another really big way that averages can bite you. It's something called the double whammy. This is what happens when there's a penalty for being wrong, but the penalty isn't the same on both sides of the guess. Just think about corporate taxes again. If a company underpays their estimated tax, the IRS slaps them with a penalty, right? But say it's 3%. But what if they overpay? Well, now they've lost the chance to invest that cash, which could have earned them a way bigger return, say 15%. You see, the cost of being wrong is totally lopsided. One mistake costs you 3%, the other costs you 15%. So in a situation like this, just aiming for the average is a guaranteed way to lose money. You absolutely have to factor in those asymmetrical risks. So what's the big takeaway here? How do we actually defend ourselves against this tyranny of the average? Well, it really starts with just being a little skeptical. Anytime someone throws a single average number at you, you've got to start asking questions. Like, hey, what different groups are being mashed together to get this number, like with the kidney stones? Or are there any of those weird non-linear effects, like we saw with the hit movie? Is there a double whammy where the costs of being wrong aren't equal? The key is to always push to see the full range of possibilities, not just that one simple, misleading number. And it really makes you think, doesn't it? Where in your own life is a simple average hiding the real story? In your health, your finances, your work. What average are you relying on that might be telling you a very convenient but a very dangerous lie?